He says, I cannot share start my video. I can't hear you.
Yes, sir. No, just a second, sir. I'll enable that part also. Just a second.
He says, I cannot share start my video.
Okay. Are you able to hear me, sir?
I can't hear you. Yes, I can, but I am unable to click to my video. It says, you cannot start your video because the host has stopped it.
Okay. Actually, let me just see why is it so. Ideally, it should not have been the case.
You do everything so well, Manoj. It's just amazing. How you do that, I can't.
Sir, actually, this video issue, I think it is most probably from the main ICT center. Let me just ask them that if they can change it. Are you able to hear me, sir?
Yes, I am able to hear you. I am able to see you. But
okay,
my video
your
is
video
not
is
on.
off. Okay, let me see. How can I? Wait a second, sir. I'll just ask them.
It says you cannot start screen share while the other participant is sharing. Can you hear me, Manoj?
हाँ एक बार राजकुमार ये संदीप इधर ही आ जाओ हाँ हाँ sure yes sir
I want to share a video not for today but I just want to see whether I can share that video.
Oh sure I'll just stop sharing it for a while. कर्सर का जो एक बार चेक करो पार्टिसिपेंट में इसकी सेटिंग में कुछ इशू है यहाँ तो ऐसा कुछ नहीं ये मेरे ख्याल से इनकी सेटिंग है ना शायद जो हमने वो बनाया पैनलिस्ट का उसमें आई थिंक कि वो वीडियो ऑफ यहाँ से हम कर सकते हैं नहीं यहाँ पे क्लिक कर मोर इसके अंदर अच्छा इसमें स्क्रीन शेयरिंग ऑप्शन देखना अनेबल हुआ है क्या नहीं हमारा मेरा नहीं क्लोज कर सर आर यू एबल टू शेयर योर स्क्रीन
हाँ हो गया
अच्छा मैं एक सेकेंड जस्ट 1 सेकेंड
ठीक है सर शेयरिंग तो ऑन है पहले
वीडियो का चक्कर थोड़ा पड़ गया यार
अच्छा नाउ आई वांट टू शेयर a screen.
Sure sir, you can just share your screen.
अच्छा now I will play the video. Please tell me whether you can see the video.
No, I am able to see the video, sir, but
you can.
We are not able to hear any sound.
No sound.
No sound. No sir.
Can you see the video?
Yes, we can see
the two balls coming together.
Yes, absolutely.
Okay. Excellent.
Sure. Actually, sir, I think maybe if you can just stop sharing.
All right.
Yes. Sir, can you try now?
My slides.
No. Just try to see now if it has been unable to share your video. Has it been enabled now? Yes.
Oh.
Okay, fine. Actually, in this we have to change the settings. So I've just told my ICT staff that we can have now from next time onwards this to be enabled for all future activities.
ये कोई लिखता है कि दक्ष बाबा सर योर नेटवर्क इज स्लो.
Network is slow. Okay. No, I don't think so. There is any network issue. Maybe Daksh, you can check it at your end. The issue could be that because it's a video, so there must be some time lag between it. Yeah, it's good.
Okay.
So they are saying it's.
Hello, Gitika, how are you? I can see Gitika's name, but cannot see her.
Yes, you must have. Actually, sir, what has happened? The number of registrations have exceeded 500. So, so I've just made it live now. So it's a live on YouTube also. Yes, yes, it's live on YouTube. So what I'll do is I'll
just introduction थोड़ा कम रखना वो मेरा बायोडाटा
yeah, sure.
हाँ 2 लाइन का रखना 2 लाइन का रखना.
No, definitely.
अच्छा एक सेकंड मैं जरा अपना स्लाइड शेयर कर लूं.
Sure, sir. Yeah, please go ahead, sir.
चलो. एक सेकंड just
sure.
Let me. Can you see the first slide?
Yes, sir. Just if you can put it in the slideshow.
Can you see
yes,
this?
Perfect. Perfect, sir.
Yeah. All good.
All good. So we will start in another 5-7 minutes. So
Sure.
I'll give a short intro, and then from 4:30 we can start. So till that time, sir,
तुम्हारा management बहुत जबरदस्त. Sorry, everyone can
Good
hear.
afternoon, sir.
Hello,
yes,
Gitika,
everyone
I've
can
said
hear it,
good
sir.
afternoon quite some time back. I did not get a reply.
Yes.
So there was some issue with my audio and video. My video is still, I'm not able to switch it on right now.
I cannot see you. I cannot see
I
you.
know.
No, actually, Ghatak, there is a problem in the
I know.
settings for this. Yes.
Not an issue.
Yeah. So, sir, if you can just stop sharing for a while, then I'll just share my screen. Yeah.
क्या करूं मैं एक सेकंड. You share.
No, sir, you just have to put stop share. Yes.
Stop share. Oh.
Yes, yes. So I'll just share my screen for a while, and then yeah. So we will just wait for another 5-7 minutes. Actually, the school students, they have a certain issue that in some of the schools, the classes, they are going on till 3:30. And in certain cases, they are over by 1:30. Some of them, they have their extra classes, or some of them, they have their tuitions. So what should be the most ideal time to conduct these sessions? So I try to take a poll from the school teachers, and they suggested.
You require a full institute with you. Full. Really, I'm not joking. I'm not joking. The amount of things that you are doing, just amazing, and therefore, This requires so much of careful thinking and planning, and it's a great contribution.
It takes lot of time, sir. But the best part is that with this technology, like we have platforms like Zoom, WebEx, so it's all very simple. You just need a good laptop and a good Wi-Fi.
Zoom is best. WebEx, NASI ke paas WebEx hai, that is not so. Ajoy, everyone can hear us?
Yes, everyone can hear you, sir. You are live right now.
Acha.
Yes.
Acha, live on YouTube also.
Yes. Tomorrow we have a session by Professor Patrick Dasgupta, and so once this will be over, then I will be sharing the link for tomorrow's session. And
Tomorrow
so
will be Dr. Patrick Dasgupta.
Yes, it will be at 4 o'clock tomorrow. Yeah, and I have requested all these speakers to kindly give a time frame between 4 to 5:30 or so that maximum students, after having a lunch, they can attend the session. And I requested each speaker to contain it within 30 to 40 minutes so that we can take up questions. And because I expect more questions, because from school students, we expect usually more questions. And
someone is asking, when will the program start? You tell that.
Yeah, I've already shared it, sir. We will start
say
it
that,
at
say that.
4:25. Yes. Okay, so you have already questions started coming now. So Hani Patel is putting this thing. Yeah, we will be, this is for a general announcement for all the attendees. We will be taking up all the questions at the end of the session. So please type only relevant questions which are related to the webinar. And please avoid good morning, hello, how are you, all these kind of messages. Yes, it will save a lot of my time in figuring it out which are the important relevant questions. Yeah.
There is one Kajal from SKV Kerala, and I think she wants that please one time introduce yourself. So I would like to introduce Professor Manoj Saxena. He is one of the most dynamic young persons, very accomplished. He has worked in the general area of electronic science for a very, very long time. He will introduce me, I guess, so you will get to know me. But who will introduce Professor Manoj Saxena? And
we don't need any introductions.
To the students, it's incredible the amount of effort that he is putting in for organizing such webinars, numerous webinars. And in fact, it was last year or this year that you organized those Nobel Laureate lectures. When was that?
Sir, it continued from last year, and the last session was in March. And I have requested these students to subscribe to the YouTube channel also. So here they can see all the previous lectures, recordings, everything. Yes. Yeah, Anurag sir has also joined. My apologies,
God.
sir.
Kahan Anurag sir?
No, he has joined.
Sorry, I cannot make any comment that.
Exactly. No, my apologies to my panelists who cannot share their videos right now because of a small technical glitch in the settings that they have allowed only the host to share the video. So the panelists cannot.
I'm trying to, they say host has not.
No, I know, sir. I actually,
I was
this
wondering
time,
what is happening.
No, this is.
Agrim Gupta has asked, what is E is equal to MC square? That is what I would like to tell you in half an hour or so, what that equation means. That is the purpose of today's talk. Sorry, Manoj.
I would say it is not MA square and MB square, it is MC square.
MC square.
There was a cartoon like that.
Yeah, there was a cartoon, I know.
So it's around 4:28. I think we can formally
What time is
start.
there?
It's about 2 minutes to 4:30, sir. Yeah. So because most of them, they have also joined from the YouTube link also. So it's their choice, absolutely, whether they would like to attend it through this or through YouTube. So a very good afternoon to all the attendees and to the distinguished speaker, Professor Ajoy Ghatak, and Professor Anurag Sharma, Chairman, NASI-Delhi Chapter, and the other panelists who are there with me in today's inaugural session for the School Outreach Program, which is jointly organized by the National Academy of Sciences, India, Delhi Chapter, and the Deen Dayal Upadhyay College, University of Delhi. This whole program is supported by NASI Delhi Chapter and also by the DBT Star College program at the Deen Dayal Upadhyay College. Today we have with us Professor Ajoy Ghatak, the President of the National Academy of Sciences, India, and Meghnad Saha Fellow of NASI, who will be talking to us about Einstein and his special equation E is equal to mc square. Before introducing Professor Ajoy Ghatak, I would first like to request Professor Anurag Sharma, Chairman, NASI Delhi Chapter, to say a few words to all the attendees.
Okay, good afternoon. Welcome to this program, which is a school outreach program, which Dr. Manoj Saxena, Professor Manoj Saxena has put up.
We cannot see you, Dr. Anurag.
I know.
Sir, that's a technical glitch.
That's a technical problem. That's what he said.
Yeah.
I cannot switch on my video. I'm not able to switch on my video.
Yes. Yeah.
So
my apologies.
Yeah, that's fine. So so welcome to this special public webinar. Seminar has become webinar these days, and I don't think you could have had a better speaker for this program for several reasons. First of all, of course, he's the president of the NASI, under the banner of which Delhi chapter of which is being organized. Secondly, he is, of course, speaker par excellence. I mean, you cannot hear better than that, a better person than that. And lastly, or probably, yeah, lastly, the least important is that he's my guru. I have done PhD with me. And so, it's several reasons that I'm very happy to be listening to this seminar. And I'm sure all of you will enjoy this seminar like anything, and it'll be a treat. So I will not say anything more. I think Manoj, you can take over now. Yeah.
Sure. Thank you. Thank you very much, sir. Professor Ajoy Ghatak is currently associated with the National Academy of Sciences, India. It is BSc from Agra College, MSc from Delhi University, and PhD from Cornell University. He has authored several books, including his undergraduate text on optics, which has been translated to Chinese and Persian. His other books include Quantum Mechanics Theory and Application, co-authored with Professor S. Lokanathan, Fiber Optics, Lasers, and Optical Electronics, all three co-authored with Professor Tyagarajan. And his most recent book is on Einstein's Gears of Miracle, E is equal to mc square, the light, quantum, and spatial theory of relativity. He is recipient of the 2008 SPY Educator Award in recognition of his unparalleled global contribution to the field of fiber optics research and his tireless dedication to optics education worldwide. The 2003 Eschler Hoffman Weller Award instituted by the Optical Society of America in recognition of his outstanding contribution to optics education. International Commission for Optics 1998 Galileo Galilei Award, and also the CSIR 1979 SS Bhatnagar Award for outstanding contribution in physical sciences. Very recently, he received the OSAR 2020 Sangso Lee Award for his seminal role in the development of fiber optics and guided wave photonics, and for pioneering optics education in India. So with these words, I now request Professor Ghatak kindly share his screen. And
can you see the first slide, Dr. Saxena?
Absolutely.
Yes, we can see.
Okay. Can I start? Is my voice clear?
Absolutely, sir.
Yes.
Okay. Thank you very much, Professor Saxena, Professor Anurag Sharma, for asking me to give the first talk in this series. We are all very fortunate to have people like Professor Anurag Sharma and Professor Manoj Saxena, and who are organizing the series of talks. And Professor Manoj Saxena has worked extremely hard for this. So all teachers and students take advantage of this. And it's a unique opportunity that Professor Manoj Saxena has created. It will make us very happy if you take advantage of all the lectures that are being organized. And I'm going to speak for about 30 minutes on Einstein and his famous equation E is equal to mc square. And this is in Einstein's own handwriting. There is a very famous book on E is equal to mc square. The title of the book, as you can see, is a biography of the world's most famous equation by David Bodanis. It's a very nice book, and you could think of reading this. I will be myself following the book that I have written on Einstein's Year of Miracles. E is equal to mc square. In his Year of Miracles, he discovered E is equal to mc square, the light quantum, which we now know as photon, and special theory of relativity. This book has been published by Viva Books. Here is the sadhu who is worshipping the light from the sun. And therefore, the question arises, who created light? And of course, all of you would say that God created light. And in fact, Genesis says that God created light on the first day. But God did not create the sun and the moon until the fourth day. So that is what the Genesis says. So I'm going to ask that what actually really happened? How long did it take to create the sun? And for that, we have to go to Einstein. And this is when Einstein was about 26 years old. And he was working in the Swiss Patent Office. And in the year 1905, Einstein, working in the Swiss Patent Office, published 5 outstanding papers. These 5 papers are often referred to as the Annus Mirabilis papers. Annus Mirabilis are Latin words meaning year of miracles. So 1905 is Einstein's year of miracles. And in fact, there is a book which is edited by John Stachel. The title of the book is Einstein's Miraculous Year, Year of Miracles. In that year of miracles, he published 5 papers that changed the face of physics. And the 5 papers were, the first one was a new method for determination of molecular dimensions. He gave a very beautiful method for finding the size of, say, for example, water molecule. How big are these? In the second paper, which Einstein considered revolutionary, he wrote that radiation energy, that is light, consists of indivisible quanta of energy. There is packets of energy, and the value of the energy is h nu, where h is the Planck's constant and nu is the frequency. And it has a momentum, which is h nu by c. So this was a revolutionary concept, because at that point of time, light was thought to be a wave phenomenon. And so therefore, his 1905 paper led to wave particle duality and development of quantum theory. In the third paper, Einstein gave a beautiful theory of Brownian motion, which involves movement of a big particle, which is shown here as yellow. And it is by continuous collisions with many smaller molecules of a gas. So because of thermal motion, they are hitting a large particle like a virus, and it moves. So this movement is known as Brownian motion. And he gave a very beautiful theory of that, which started the field of statistical physics. In the fourth paper, he put forward the special theory of relativity, which implied that time is not absolute. For example, if you go on a very fast aircraft from here to Bombay and come back, from Delhi to Bombay and come back, your watch will be slightly different from your friend's watch who is stationed in Delhi. So time is not absolute. This was a profound concept that he put forward. And in the fifth paper, he wrote down the famous equation. He derived the famous equation, which I'm going to discuss today, E is equal to mc square, that matter can be converted to energy and the energy can be converted to matter. So here is my granddaughter, who is on the back of the statue of Einstein at Frankfurt Airport. And beneath the right hand of Einstein in the statue is a book. And if you expand this, the title of the book is E is equal to mc square. So as you can see, this is the most famous equation that Einstein wrote down. About his 1905 papers, the 5 papers that changed the face of physics, Einstein later said, a storm, as if a storm broke loose in my mind. So let us consider 2 magnets. Each magnet weighs exactly 1 kilogram. The North Pole is facing the South Pole of the other magnet, so they attract and they join together. So when they join together, its mass is not 2 kilo, it is slightly less than that. The total mass of the 2 magnets stuck together will be slightly less than 2 kilos. Let us suppose it is 1.999999 kilo. That is, let us suppose that the mass decreases by 0.1 nanogram, 0.1 billionth of a gram. It is even less. For most magnets, the loss of mass is even less. So we assume, this is an assumption, that there is a small loss of mass. It could be 10 to the power of minus 11 grams. But let us suppose it is 10 to the power of minus 10 grams. So 10 to the power of minus 10 grams, as you all know, is 10 to the power of minus 13 kilograms. And so therefore, according to Einstein's equation E is equal to mc square, the energy released in the process is equal to loss of mass multiplied by the square of the velocity of light in vacuum, where c is the velocity of light in vacuum, which is 300 million meters per second. As you know, it takes about 1 second for light to come from moon. It takes 7.5 minutes or 8 minutes to come from the sun. So if you multiply this quantity, which is 10 to the power of minus 13 kilograms, multiplied by the square of the velocity of light, then the units are joules, that is the MKS units of energy. So if 2 magnets hit together and there is a loss of mass of 1/10 of a billionth of a gram, then the energy that will be released is about 9,000 joules. What is 1 joule? I'm sure all of you know this. For example, a 100-watt light bulb gives out 100 joules of energy per second. So joule is an unit of energy. Thus, if the total mass of the two magnets becomes 0.1 nanogram less, it will require about 9,000 joules of energy to separate them, creating a tiny amount of mass. So let us suppose what I am trying to tell you here is that the two magnets are stuck together and you separate them. To separate them, you have to apply, if you have to do some work, you have to apply certain energy. If it is very rigidly stuck, you will have to apply a lot of energy. But if the loss of mass has been 0.1 nanogram, then it will require 9,000 joules of energy from your muscles to separate them. And when you separate them, you create a very small amount of mass. And in this case, about 0.1 nanogram. So that is the basic implication of the equation E is equal to mc squared. So let me give you another example. As you all know, any atom consists of a small, tiny nucleus which has protons and neutrons inside it, and surrounding the nucleus are electrons. So this is a lithium atom which has 3 protons, positively charged protons, and the nucleus of lithium atom consists of, let us suppose, 3 protons and 4 neutrons. Neutrons are neutral, and there are 3 electrons which are orbiting surrounding. So the simplest nucleus is the deuteron nucleus, heavy water. Some of you may have heard that. That is deuteron, deuterium atom, which consists of 1 proton and 1 neutron. The nucleus of deuterium atom consists of 1 proton and neutron stuck together. So if you separate them, they are held together by nuclear forces, which are attractive, like 2 magnets. So when they are stuck together, their mass is slightly less, as I have tried to tell you from the magnet experiment. So if you put 1 proton and 1 neutron on one side of a balance, then that, if they are far away, then that will weigh little more than the proton and neutron stuck together. And if I have 1 proton and 1 neutron, if you allow them to join, when they stuck together, then as in the case of magnets, a small amount of energy is released. And this energy is 2.23 million electron volts. And 1 million electron volt is also an unit of energy. For example, you have a unit of length. You can measure it in centimeters or meters or inches and foot. There are 2 different units of the same thing, cell length. Similarly, joules is a measure of energy. So is MeV. And 1 MeV is about 1/10 of a trillionth of a joule. In nuclear physics, one uses million electron volts as the unit of energy. So you must have read in your books that proton and neutron are fundamental particles. And if you add their masses, then this will come to 3.3475517 10 to the power of minus 27 kilograms. On the other hand, the mass of the deuteron nucleus, which consists of proton and neutron, which are stuck together, 2 magnets stuck together, that is almost the same, but slightly less. You can see this is 3.347, this is 3.343. So the difference in the 2 numbers is known as mass defect in nuclear physics. or loss of mass. The quantity of matter is the same. You have proton and neutron which are separated, and then when they are stuck together, their mass is slightly less. And the difference of the mass is mp plus mn, which is this, minus the mass of the deuteron. That gives us 3.9657 in 10 to the power minus 30 kg. This is 10 to the power of minus 27 kg. So the energy that will be released when a proton and neutron get stuck together and forms the deuteron nucleus is loss of mass multiplied by the square of velocity of light. That is what my Einstein's equation tells us. So I substitute the loss of mass, and this is 3 into 10 to the power of 8. Square of that is 9 into 10 to the power of 16. If I multiply that, I will get 3.569 into 10 to the power of minus 13 joules. And this is 2.23 million electron volts. As I told you earlier, million electron volt or electron volt is also another unit of energy. In nuclear physics, one uses million electron volts as the unit of energy, which is equal to 1.6 into 10 to the power of minus 13 joules. So therefore, if I have a deuteron nucleus in which you have proton and neutron stuck together, then you will have to supply a certain amount of energy to separate them. So a tightly bound system goes over to a loosely bound system, for which you will have to supply some energy, and through that you will create a small amount of mass. Because in my previous slide I showed that the mass of the proton plus neutron put together is slightly more than the mass of the deuteron. You can show that this is the mass of the proton and neutron stuck together in deuteron. So this is more than this. So when a tightly bound system goes over to a loosely bound system, you create a small amount of mass. And conversely, when a loosely bound system goes over to a tightly bound system, certain amount of energy is released and there is a small loss of mass. This relationship between loss of mass and creation of energy is what E is equal to mc square means. This is, some of you may have heard, this is the Bohr model of the hydrogen atom. Now, in the Bohr model, which is really an old model, you have a proton, positively charged proton sitting at the center. And the electron rotates in a circular orbit, in discrete orbits, something similar to an Earth rotating around the sun. So these are known as Bohr orbits, which are circular in nature. So different energy states of the hydrogen atom. The hydrogen atom consists of a proton and an electron which is rotating in a circular orbit. When an electron in a higher orbit makes a jump to a lower orbit, it goes to a state of lower energy. And it emits a light quantum. It emits a photon that Einstein had said. And the energy of the photon is the difference of the energy of the two states. And this energy, as I had mentioned earlier, is equal to h nu, where h is the Planck's constant and nu is the frequency of the light that is coming out. So therefore, the electron, which has a very well-defined mass, is rotating in this orbit. It goes to a lower orbit and emits a radiation. The hydrogen atom consisted of one proton and one electron before and after. The quantity of matter is the same, But the total energy of the atom has reduced because it has emitted a photon. And so therefore, its mass must also reduce. So this is the energy of the photon or the light quantum that is emitted. This is how light is emitted from atoms. So delta M, change in mass times c square, is the energy. So the value of Planck's constant is 6.63 into 10 to the power minus 34 June 2nd, into the frequency of the light that is emitted, which is 2.47 into 10 to the power of 15 hertz, divided by the square of the velocity of light. So if you calculate this, then you will find that the loss of mass, this is loss of mass, is equal to 1.8 into 10 to the power of minus 35 kilograms. This is, of course, a very tiny mass. It is about a billionth of the mass of the proton. So what I wanted to tell you in this diagram, this is known as the Bohr model of the atom. Some of you may be knowing this, which was put forward in 1915 or 14 by Niels Bohr, Nobel laureate, and in which the electron, which goes around in circular orbits, it jumps to an orbit of a smaller radius. So it goes from a higher energy state to a lower energy state and releases a light image. But the quantity of matter is still the same, but the energy has reduced. And so therefore, its mass, if I weigh the hydrogen atom, it will be less. So actually, I wanted to show you this photograph. Niels Bohr had come to Delhi University in 1959. So there is Professor Niels Bohr. He gave a beautiful lecture. There is myself, there is Professor Mitra, Professor Aulak, great people of Delhi University. So in 1905, after he worked out this paper, he wrote to his friend Conrad Habit that light carries mass with it. The argument is amusing and seductive, but for all I know, the Lord might be laughing over it and leading me around the nose. So when he wrote that paper, he himself did not believe. And it was only in 1930 that this equation was verified experimentally through nuclear reactions. So here is a fusion reaction. Now understand this. This is the deuteron nucleus. Deuteron nucleus, which consists of a proton and a neutron, positively charged proton and a neutron. This is a tritium nucleus, which consists of proton and two neutrons. They fuse together. It's like a chemical reaction. And you have neutron and an alpha particle. Now, alpha particle has two neutrons and two protons. So you see, the daughter products, that is neutron and alpha particle combined, have 3 neutrons and 2 protons. This also has 3 neutrons and 2 protons. So the quantity of matter remains the same. But this alpha particle is a very tightly bound nucleus. Its binding energy is very large. As I had told you earlier, the binding energy of deuteron is about 2.23 million electron volts. So this binding energy, to separate them, it requires 2.23 MeV of energy. To separate the tritium nucleus, it requires 8.48 MeV. So that the total binding energy, if you add these two up, it will be 10.7 MeV. That is, if these 5 particles are completely made free, then you will have to supply 10.7 million electron volts, creating a tiny amount of mass. On the other hand, the alpha particle is very tightly bound. It requires an enormous amount of energy to separate them. How much is that energy? 28.3 MeV. And so therefore, the neutron is free. So there is a gain in binding energy. A loosely bound system goes over to a very tightly bound system. And so therefore, the difference of the two, 17.3 or something like 17.6, is released in the form of kinetic energy of neutron and alpha particle. One can do the simple kinematics. The neutron energy is 14.1 MeV and the alpha particle energy is 3.5 MeV. So what is kinetic energy? That is heat. So therefore, one thing that you should remember, that this is positively charged, this is positively charged. So they will repel when they come close to each other. So therefore, this is a typical fusion reaction. And so therefore, it requires a very high temperature for fusion reaction to occur. Millions of degrees Kelvin. So fusion reactions do not occur in the room temperature, or very, very, very rare. Only if you have a heated body, then you have fusion reaction. Such fusion reactions, as I told you, require very high temperature. Now, such fusion reactions, as most of you would know, are happening inside the sun, because of which it has become very hot. And it starts radiating light. The light that you receive on Earth is because of the fusion reactions. It becomes so hot that it starts glowing. So our sun is like a 400 trillion watt light bulb. It is emitting a large amount of light. So therefore, it emits 400 trillion joules of energy per second in the form of light. Is very small part we receive on the surface of the Earth. So the question is that I would like to ask you is that because it is emitting so much of energy, is its mass becoming smaller? Because Einstein said that energy can be transformed to mass and mass can be transformed to energy. So you have a tremendous amount of energy coming out in the form of light. So my question to you is whether it is the mass of the sun is reducing. The answer is of course yes. And the amount of energy that I just now said can be easily calculated from the fact that the distance of the sun from the Earth is about 150 million kilometers. And on the surface of the Earth, we receive about 1350 joules per second per square meter, multiplied by 4 pi r square. So that is 4 into 10 to the power of 26 joules per second. 4 trillion joules per second. That is the total amount of energy that is liberated by the sun. And so you have this equation E is equal to mc square. So therefore, mass of the sun that is continuously getting converted to energy is energy liberated by the sun per second divided by c square. So energy liberated by the sun per second is 4 into 10 to the power of 26 joules per second divided by 3 into 10 to the power of 8 whole square. If you divide that, you get 4 billion kilograms per second. So if you had a machine to weigh your sun, what is the mass of the sun, then every second, the mass of the sun is reducing by 4 billion kilograms. That's a huge amount of mass that is getting converted to energy. You know, in the Hiroshima bomb, half a gram of matter was converted into energy. In the Hiroshima atomic explosion. Kya time ho gaya? Oh my God. I'll take 5 more minutes. Is that okay, Dr. Saxena?
Yes,
Thus,
sir.
every year, about 120,000 trillion kilograms of mass is continuously getting converted into energy. So how did the sun appear? So it was a huge cloud of dust And slowly, the gravitational attraction, it consisted of hydrogen atoms, it contracted. And as it contracted, a loosely bound system goes over to a tightly bound system. And therefore, energy was released. It got heated up. And now it is, after about 4.5 billion years, we have a sun which has a surface temperature of about 6,000 degrees Kelvin. So it became so hot that the inside became about millions of degrees Kelvin, and fusion reactions started happening. And the temperature inside the sun is about 15 million degrees centigrade. The density is 160 grams centimeter, and pressure is so much. They say that because of theoretical physics, we know much more about the inside of the sun than the inside of the earth. So eventually, when the sun loses all its nuclear fuel, it will expand. The gravity will not be able to hold it together. It will become a red giant in about 5 billion years. And then it will be again a collapse and form a white dwarf. My time is up. So it is an equation similar to this that happens inside the sun. Essentially, 4 protons go over to a very tightly bound alpha particle, and positrons, because proton is positively charged, neutron is neutral. So you require 2 positrons to balance the charge. And this is the type of reaction that is happening inside the sun. The theory for that was given by Professor Hans Bethe, who was my teacher in Cornell University. He taught me 2 courses on quantum mechanics, an amazing man for his contribution to the theory of nuclear reactions. So David Bodanis writes, it is as if when God created the universe, he had said, I'm going to put X amount of energy in this universe of mine. I will let stars grow and explode. There will be fires, explosions of volcanoes. Despite all the variations, the total amount of energy will remain the same. The amount I created at the beginning will not change. There will be not 1/1,000,000th part less than what was there to start. So all this plus a derivation of the equation, my time is up. It is half an hour already. So it is given in this book. So the title is Einstein's Year of Miracles, E is equal to mc squared. And I've given a very simple derivation of the equation E is equal to mc squared. And the light quantum, the photon, what is it, and the special theory of relativity. Thank you, Professor Saxena and Professor Anurag Sharma. Thank you very much.
Thank you very much, sir.
Thank you, sir.
There are a few questions which are there from the YouTube, as well as there were about 100 plus attendees there on the YouTube also.
Where are the questions?
Also, sir, there are questions and comments. So I will just take up 6 questions.
What I will do is, can you give me the link to the YouTube?
Yes, sir, YouTube, I am just correcting it. There are questions which are there in the chat section. So if you can just stop sharing.
I have to first stop sharing. Sorry.
Yes.
Sorry.
Yes.
Is it all right now?
No, sir. You have to stop sharing. I guess still able to see your screen. Yeah.
Okay.
It's going.
No, it's still there.
Still there. Sorry.
Something has changed.
ये क्या हो गया? New share. It doesn't say stop share. Oh, sorry, sir.
Yes.
So how do I go to YouTube?
So there is a chat. Okay, you want to see the questions on the YouTube?
No, whatever the questions are.
Okay, so there is on the chat section, sir.
Oh, okay.
There is a chat. Yes.
Red giant will be lighter but shiner and hotter than the sun present. No, 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 no. It will be cooler. It will be much cooler. It is a red color. So red giant will be much bigger. It will envelop the whole earth. Life will cease to exist. It will be, you see, when the nuclear, when almost all the hydrogen get converted to helium, so it will be lighter because, as I told you, it is losing 4 billion kilograms per second, 120 trillion kilograms per year. It is losing. So it will be lighter, it will be cooler, and it will become a huge red object. So red, the temperature is much smaller. Can we get a recording of this minute? That is Professor Anurag Sharma, Professor Manoj Saxena will tell. Sir, if sun is losing energy, then why it is becoming larger? Oh, it is becoming larger. Right now, it is in a steady state. So you do not see the change in size. But eventually, when it burns out all the energy, then so much mass, the gravity will not be able to hold it together. What holds it together right now? It is the gravitational pull. You see, I showed you one slide, probably it was in a bit of a hurry. So you have a large, what God created was a large number of hydrogen atoms. 15 billion years back, what did God create? A large number of hydrogen atoms. Now, these hydrogen atoms, this is the gravitational attraction between the atoms which make it collapse to form a star. So as it collapses, a loosely bound system goes over to a tightly bound system. Loosely bound system goes over to a tightly bound system. And so therefore, from Einstein's mass energy equation, it gets hotter and hotter. And it becomes so hot, 1 billion degrees Kelvin, that fusion reactions start happening. And then it is in a steady state, which is right now the sun is. Eventually, most of the hydrogen atoms will be converted to helium atom, and it will start cooling down. And also the gravity will not be able to hold it together. So it will expand. And it will expand to form a red giant. And then there again will be a gravitational collapse, at least for the sun. If the sun had a much higher mass, it will converge to a black hole or a neutron star. But the sun, our sun, will most probably collapse to a white dwarf star. And I thought I must mention that the theory of the white dwarf star was given by Professor Chandrasekhar, an Indian. He was a nephew of C.V. Raman, but he did his work in US and UK. So that is the answer. What will happen if an object travels at the speed of light? You see, an object can never travel with the speed of light. It can approach the speed of light, but it can never travel with the speed of light. So the mass, the rest mass, for example, the mass of the particle is given by m0 divided by under root of 1 minus v square by c square. So the mass becomes larger and larger. But it can never have an exact speed of light. PDF to us, everything is given in that book. Maybe Professor Saxena, as I mentioned to you in the morning, if the book can be made available, probably if you can just write to them the place or something like that.
Sure, sir.
I wish I had the time to tell you about the derivation of the E is equal to mc square. That is also very nice. If proton and neutron goes to deuteron, then could deuteron gain mass? No. You see, what I tried to say, someone asked me, Papia Bhadra, that proton and neutron forms deuteron. What is the deuteron nucleus? Which is proton and neutron stuck together, like two magnets getting stuck together. So therefore, the mass of the deuteron is slightly less than the proton and the neutron put together. Okay, I've been only learning derivations, but do you have any suggestion as to how to come up with them? So that will take half more hour, some other time maybe, how to derive, but it is given in the book, a very simple derivation. How sun lose their energy, how sun loses its energy. It is in the form of light, heat, radiation, photons. Photons carry energy. You put your hand on the sun, your hand gets hot. Why? Because the photons carry energy, and the energy is absorbed by your hand or your skin or your face, and you feel warm. So therefore, the sun is losing energy. The sun, inside the sun, oh, I made a wrong statement. Inside the sun, a lot of mass is continuously getting converted to energy. What form of energy? Light. Light, the number of neutrons and protons are roughly remaining the same. But because of the fusion reactions, one fusion reaction I had told you, 4 billion kilograms of mass is continuously getting converted to energy. So that is how sun loses their energy. Sun loses energy because a loosely bound system is going over to a tightly bound system. Fusion reactions means you create alpha particles, and so therefore, but the number of neutrons and protons are remaining the same. Ice age later, eventually it will become, the sun will become cooler, it will become a white dwarf, and then it will cool down. So, chala. What are the postulates of the Bohr model of the atom? The Bohr model of the atom was that like the earth goes around the sun, similarly, the hydrogen atom, he gave a very beautiful theory of the hydrogen atom, in which he said that the proton is at the center. Actually, that also moves, but the proton is very much heavier than the electron. So that moves, that rotates in circular orbits. And then he made a postulate. Postulate means it is an assumption. There is no proof of that. That the angular momentum is a multiple of h over 2 pi. How did he make that? That is the genius of Niels Bohr. And so therefore, the orbits are discrete. The orbits are discrete. So one orbit is about, say, half of A0. A0 is 10 to the power of minus 10 meters. So next one is 4 times that, next time is 9 times that. So these are the discrete orbits. Now when the electron is rotating in the smallest orbit, it is said to be in the ground state of the hydrogen atom. Then there are higher excited states. So when the electron rotating in a higher orbit goes over to a lower orbit, it emits a photon. It emits light. It emits energy. And where does this energy come from? Because the atom goes over from a higher energy state to a lower energy state. The atom still consists of 1 proton and 1 electron. Something like that. So I have answered most of the questions. Okay, sir. So it releases mass and energy in the form of heat. No, it is not that. Mass gets converted to energy. Mass gets converted to energy. And energy can also get converted to mass. As I told you, for example, I have a deuteron nucleus. Its mass is something. Now they are stuck together like 2 magnets. I pull them apart. So when I pull them apart, if you pull 2 magnets apart, then you have to do some work, supply certain energy. When you supply that energy, you create a mass. So the Einstein's mass energy relation tells us that energy and energy can be converted to mass and mass can be converted to energy. Okay. There is someone, Debashi, Antara Banerjee. Interesting lecture. I'm so glad you liked it, Antara. Oh, if you can destroy 1 kilogram of mass, you will get a tremendous amount of energy. Tremendous amount of energy. As I told you, in the Hiroshima explosion, half of a gram of matter was converted to energy. Okay. Dr. Professor Saxena, shall we close it here?
So maybe you can if you wish to, then you can take up 2-3 more questions and then.
How can we learn quantum mechanics? By studying. I can give a course of lectures on quantum mechanics. Someone says, how can we learn quantum mechanics? It's one of the most beautiful subjects. And let me give you a Feynman quote. Feynman, Richard Feynman, Nobel laureate, and one of the greatest theoretical physicists ever born. He said, no one understands quantum mechanics. And why? Because quantum mechanics tries to explain to you the interference experiment in which light passes through 2 holes and produces this interference pattern. Not only light, but also electrons also produce this interference pattern. And light also consists of photons. And you can have single photon, single electron experiments. And you explain that by saying that electron is characterized by a wave function which is present in both these holes. So it passes through both the holes simultaneously. And does it split? No, it does not split. It is at both places. And it interferes with itself to create a probability distribution, which is the interference pattern on the screen. I have tried to explain this very clearly in my book on optics. So I have very, very carefully tried to explain this. So that is the whole quantum mechanics. And Feynman says the entire concept of quantum mechanics is contained in the 2-hole Young's double slit experiment, interference experiment. Some of you may have already done the double slit experiment and things like that. Chala.
Okay, sir. I think there is one question which the person is asking again and again. What happens when transition of electron takes place from first to infinite orbit?
Oh, no. A transition cannot take place from ground state to infinite. You have to supply an energy. For example, let me make it clear that if you have the electron in the lowest orbit, you want to make it free, then you have to supply a certain amount of energy. What is that amount of energy? It is about 13.6 electron volts. This is known as the ionization energy of the hydrogen atom. So the electron gets completely detached from the hydrogen atom. So you have mass of the proton and plus. So you supply energy and you create mass. Something like that. No. This is for sure. Is that the question, Professor Saxena?
Yeah. Yes, sir.
Okay.
And I think this question answer session will go endless because the questions.
Pragya Prakash Lenka says that, sir, what happens when transition of electron takes place from first to infinite orbit? That is not a transition. Transition takes place from a higher orbit to a lower orbit. Then light is emitted. But if it is from a lower orbit to a higher orbit, that is absorption. And light, external light, the hydrogen atom or any other atom. You see, for atoms, you have emission spectrum and also absorption spectrum. You see, some of you may have read that when you view the solar spectrum, you get Fraunhofer lines. The light that comes from the sun hits the atoms and it takes from a lower state to a higher state, and that line gets absorbed and you get dark lines in the spectrum. Maybe someday I will tell you about the spectrum. Beautiful. What the study of spectrum leads to. It leads to tremendous discoveries. So to the answer, Prangya, that what happens when transition of the electron takes place from first to infinite orbit. So that is not a transit, that is an absorption. So there must be some incident energy. It could be in the form of light. The hydrogen atom absorbs, takes that energy, the electron jumps to become free. So then electron being in a bound state, from a tightly bound system, it goes over to a loosely bound system, create mass. Therefore, a tiny amount of mass is created. So that is the how to learn quantum mechanics. I already told you. And
so there is one question from the YouTube also I would like to take up as those students. Yeah, he's asking, can red giant cause heat wave?
Say that again. Which
can red giant cause heat wave?
Cause heat?
Heat wave.
I can't follow. Red giant emits red light approximately.
Yes.
Okay. Yeah, those are in the red end of the spectrum. When you heat a plate, iron, this thing, it becomes red hot, and then it will become white hot. And of course, before that, it will melt probably. But in general, if a body is at the surface of the sun, the inside of the sun is at 1 million degrees Kelvin. And I had another slide which I showed, in which I don't know why I didn't get that. That I showed that today lasers. You have this is the Shiva reactor. Shiva had 8. I mean, according to the Americans, Shiva had 8 arms. So there are 8-arm laser beams focusing to a narrow space and creating fusion reactions. So right now we can have fusion reactors, but the energy that is required to pump in the laser is more than the energy that you get out of the fusion reactions. But they say that it will take 10 more years to have that energy that is liberated from the fusion reaction is more than the energy that is required to pump the laser beam. When that happens, you will have an inexhaustible supply of energy. That is the fusion energy. That Nimai Swami, you have said how to learn quantum mechanics. I have a set of video lectures on NPTEL. There are many video lectures by Professor Balakrishnan of IIT Madras and many others. I have also given a course of 41 lectures on basic quantum mechanics. And fortunately, now the students have the technology in front of you. If you go to YouTube, the best lecture on quantum mechanics is by Feynman. You listen to Feynman's lecture on uncertainty and probability. He gave a course of 6 beautiful messenger lectures at Cornell University in 1964. I did my PhD from Cornell University, and one of my greatest regret was that I never could listen to the messenger lectures. Now, courtesy YouTube, I can listen to it as many times as I like. So you have now, the younger generation now has the entire technology. You go to YouTube and there are so many beautiful lectures on relativity, on E is equal to mc square, and quantum mechanics. You just have to search for them. So that is how you can learn quantum mechanics. Sorry. And of course, you have to work hard. Okay.
Thank you very much, sir.
Okay.
Yes, so we are closing the question answer session for today. I've also shared the video link for the lectures, which you can see it from YouTube. So I request Professor Anurag Sharma, who's the chairperson of the NASI-DDUC chapter, to say a few words before I ask one of my panelists, Dr. Poonam, to give a vote of thanks.
So what can I say? Beautiful lecture, and as usual, I have heard so many times. I mean, all my life I've heard Professor Ghatak's lectures,
Too much.
and I still keep learning whenever I hear him. So thank you very much, sir. And I'm sure a lot of others, listeners and attendees have benefited from your lectures. Thank you very much for this treat again.
I have one. Thank you, Anurag. There is one question, Ajanta. When two particles are getting stuck, there is slight loss of mass. But can it be determined from which particle? There is no. That is not possible because it is the combined thing that loses mass. The total mass, if you weigh, when the neutron and proton are stuck together, it is not that the neutron loses mass or proton. The combined system loses mass. You see, when I gave you that example of magnet, you see, there are no atoms or these things that are lost. They are just from a tightly bound system, loosely bound system, they go to a tightly bound system. And therefore, there is a loss of mass. Thank you. Okay, Poonam.
Thank you so much, sir. Thank you so much for such a wonderful lecture. It was so pleasant and so pleasing to hear you again explaining so enthusiastically with all these school kids. The kids have also been responding very enthusiastically, and there were so many questions and you answered so many of them, to the extent that even after a formal thank you from Professor Anurag Sharma, you still went ahead with answering. So that shows your enthusiasm, that how much you are still connected with your subject, how much you are connected with your students, and how much eager you are to impart your knowledge to these students. So it would be very a great opportunity for the students also to be benefited from such kinds of interactions. And I think they can interact with you if you would share your email ID with them. Probably some of them can send their questions to you also.
All right.
I once again thank you, sir, so much. It's always a pleasure to hear you. Thank you so much, Professor Anurag, sir. Thank you so much, Professor Manoj. Thank you, Ghatak, for being with us. And last but not the least, a very big thank you to all the attendees on Zoom as well as on YouTube for making this lecture, this event, this inaugural lecture of this continuous series of interaction with the school students, a very big start. Thank you, everyone. Thank you so much.
Thank you, Poonam. Thank you very much, sir. Thank you very much, all the attendees. I am just taking a formal permission from Anurag sir and Professor Ajoy to close the session for today. Okay. And I invite all of you to join us for another interesting webinar scheduled for tomorrow at 4 p.m. by Professor Patrick Dasgupta. And see you all tomorrow at 4 p.m. Thank you very much, sir.
Okay, bye. Thank you, sir.